All right, so today I'm going to talk about some connections of Krylov matrices to some other matrix structures and decompositions. This is inspired by a homework problem from the linear algebra class here, CS 515. And the problem is as follows. So to state the problem first, I want to define a Krylov matrix. So given a matrix, a square matrix A, and a vector B, the Krylov matrix is defined as follows. Each column of the Krylov matrix is just a different power of our matrix A times our vector B. This is exactly the set of columns that we use to construct the Krylov subspace, which a lot of algorithms use. Okay, and we're going to look specifically at the QR factorization of a Krylov matrix. Okay, so to state to make this statement that we prove in CS 515, we want to talk a little bit about the Arnoldi process. The Arnoldi process, given matrix A and vector B, the Arnoldi process constructs an orthonormal set of vectors, or basis rather, for the Krylov subspace, which is just the column space of this matrix, for call space of the Krylov matrix. Okay, and that orthonormal basis is a set of vectors Q that satisfies this, where the Q are orthonormal columns and H is an upper Hessenberg matrix. So and we will refer specifically to the upper J by J block of this upper Hessenberg matrix. Okay, with those preliminaries, we can talk about exactly what this CS 515 homework problem was. If we let Q tilde J, Rj be the QR factorization of our Krylov matrix, then we can relate the Q factor and the R factor specifically to the Arnoldi process information related to this Krylov matrix K. Specifically, the Q factor in the QR factorization is exactly the Q factor in the Arnoldi Hessenberg factorization. I should add the detail that this is upper Hessenberg. And the R factor is actually a Krylov matrix constructed from that upper Hessenberg piece, and the standard basis vector. For this to hold, I should add, we want to assume that B is a unit vector. That's just required so that I can write this, we'll see in a bit, without having to write a scaling factor everywhere. All right, so let's prove this claim. So let's assume that we have Let's assume that we have the result for j minus 1, and we're going to ignore the base case. The base case is sort of trivial, and we'll just proceed from here. So what do? Let's multiply, we're assuming this, so we know it's true. Let's multiply both sides by A, and then construct a new matrix from that by inserting a new column B at the front. Okay, so new column, this is equal because A times this equals A times this. Okay. Then one neat thing is that this matrix here is simply the next Krylov matrix. You always start a Krylov matrix with the vector, and then everything over here is just what it would be here, but with the power of A increased by 1. Cool. Next step is to note that because we are running the Arnoldi process with respect to the vector B and the matrix A, we know that B is simply the first. B is exactly the first column of our Q matrix. The first Q vector in the Arnoldi process, you just take to be a unit version of the vector B, but we designated B to be a unit vector, so we just have that B is exactly the first Q vector, the first column of the Q matrix. So we can substitute that in here. Okay, cool. Next, what do? We note that this factor here, this term here, we can think of, because of the Arnoldi process, we can think of it as instead Qj Hj. So next line we have that this is Qj times the vector E1, and then this is Qj Hj Rj minus 1. And it's all equal to Krylov matrix Kj on the right hand side. Cool. Next we factor out that Qj on the left hand side, and then we are quite close. Now we started by assuming this, so by induction all we need to do is show that the jth Krylov matrix has the QR factorization that we want. So we just need to show that this is upper triangular. We already know this is a set of orthonormal columns. Once we show this is upper triangular, we will have found a QR factorization for the Krylov matrix. And by uniqueness of the QR factorization, we'll be done. So we need to do two things. One is show that this is upper triangular, and then the next thing is to show that it actually has the form that we want it to, which is to say this form. We've already accomplished this piece, that the Q factor of the QR factorization is simply the Arnoldi vectors. We've already established that, assuming we can show that this is upper triangular. So now let's show that this is upper triangular and then show that it has the form we want. Okay, fine. By induction, we know this. J minus 1, so this is J minus 1, so this is J minus 1, E1. Okay. Let's see. So my claim is that we were multiplying this by Hj in front. Hj is a j by j plus 1, I'm sorry, j plus 1 by j. Upper Hessenberg matrix. Note that as you construct H during the Arnoldi process, constructing hj from hj minus 1, all you do is alter the rightmost column. So everything to the left of the rightmost column is simply hj minus 1, the way it was before. So we can use that to think of this as hj minus 1. And then we need something here. And then we need a new vector on the right-hand side. And then all of this is zeros. Okay, because of this, we can think of this multiplication the same way we thought of this multiplication. Multiply A by the Krylov matrix with respect to A. I'm being sloppy with notation here. I should have denoted that this k sub j minus 1 is taken with respect to A. When you multiply it in the front by A, you get basically a new Krylov matrix when you append this column vector B on the left. So over here, we're talking about kj minus 1 is specifically with respect to this hj minus 1. And what we're trying to show here is basically that left multiplying by hj has the same effect as left multiplying by this h bar j minus 1. And the key is in recognizing that because this vector only has a non-zero at the topmost entry, this vector, because this is upper Hessenberg, has non-zeros only in the top 2 entries. The next vector has non-zero entries only in the top 3 entries, and then so forth on down. Multiplying by the next H matrix, the next Hessenberg matrix, preserves that structure. So the rest of the details here are not particularly interesting. So I'll note that this is the thing we are trying to show, and all it involves is, so if I write this out, E1 h bar j, E1 h bar j, j minus 1, E1, okay. All we need to do is show that this vector is the same as this vector times h bar j minus 1. That's really all we need to show. And then show that that holds for each individual column. And I claim that it's not too hard to show that this vector times h bar j minus 1 is the same as this vector. And the same is true for the other powers. Okay, so that completes the proof that R is related to the Hessenberg form, the way that the claim stated it is. The statement is messy when you assume, the statement is messy when you don't assume that the Krylov matrix is n by n. If we assume we carry out the Arnoldi process all the way until this is n by n, this is n by n, this is n by n, then the statement is much simpler. You just have that this is the Arnoldi-Hessenberg factorization. This is the full n by n Krylov matrix, and then the statement is this Q is the same as that Q, and R is simply the Krylov matrix for H, which is kind of neat. Cool. Okay, and then, okay. So then we're going to talk about, next thing we're going to talk about is a particular Hessenberg matrix that has some neat connections here, and that will serve as a bridge to a couple, to another topic that has a couple neat points. All right, so to get there, let's first define a companion matrix. For a degree n monic polynomial, polynomial px It's monic, so I'm just writing the degree n term here with a coefficient of 0. I'm sorry, a coefficient of 1. Okay, so the companion matrix for any degree n monic polynomial is an upper Hessenberg matrix. It actually has a good deal more structure than an upper Hessenberg matrix. It looks as follows. So you can, some people define the companion matrix as the transpose of this, or with this column vector instead along the top. You can see it multiple different ways. This is the way that I'll present it. So note, because this identity matrix is one down from the top row, this is in fact upper Hessenberg. It's also a good deal more structured than that. I'm sorry, by C I meant P. There we go. All right. All right, so then the claim is that if we take P of x to be the characteristic polynomial of A, and we let C be the companion matrix, and we let K be the Krylov matrix with respect to A and with respect to any vector B, then the following holds. Which I think is, we will see, has some cool consequences. All right, so a quick proof of this. On the left-hand side, what do we have? We just have n different increasing powers of A times our vector B. On the right-hand side, what do we have? We have the Krylov matrix. And then when we multiply by our companion matrix, what are we doing? We're multiplying by this shifted identity matrix. And then we've got this vector of polynomial coefficients here. Okay, when we multiply by this shifted identity matrix, really we're just grabbing the first column here multiplied by this is really just the second column of the Krylov matrix. And the second column is this, which matches up with that. So that works out. And it turns out the other columns work out as well. That really just leaves the last column to compute. This last column times the Krylov matrix is what exactly? Well, it's supposed to be equal to A to the n times B. So let's compute this. Last column here, we want A to the n times B to be equal to these polynomial coefficients taken from over here are multiplied by the appropriate columns here. And really, this topmost entry is P0, and we're multiplying it by B times A to the 0. The next entry down would be P1, and we're multiplying that by A to the 1 times B. So it turns out that we are just matching up polynomial coefficients with corresponding powers of A. Now if we add this to the left-hand side, what do we get? This is exactly the matrix A plugged into the polynomial P times the vector B. But the characteristic polynomial with A plugged in is 0. Well, that's exactly what we expect it to be, taken from, if we add this to both sides to move it over here, then we would expect the 0 to be at the other hand side. So this completes the proof that this equation does in fact hold. All right, now we get into some neat consequences of that. The first consequence is that if the Krylov matrix is invertible, then we have that the Krylov matrix gives a similarity transformation of the companion matrix, so that a matrix A is always similar to, not always, a matrix A can be similar to the companion matrix of its polynomial, is what this proves. Okay, so that leads to the question, when is a Krylov matrix invertible? And that turns out to be when the nth Krylov subspace is full rank, or has dimension n rather. And that turns out to be when the minimal polynomial is equal to the characteristic polynomial. But that's outside the scope of this. All right, so one other consequence or thing that I want to point out. So before we were talking about the Arnoldi factorization. Where H is upper Hessenberg and Q is unitary. Okay. And then here we've been talking about the companion matrix. I'll call it companion factorization. Where, sure, C is upper Hessenberg, but it's more than that. It's more structured than that. So I'll write that it's structured. And K is Krylov matrix. All right, so H and C are both Hessenberg. K is a Krylov matrix. Q is a basis for the Krylov subspace. So here we have two different bases for the Krylov subspace. One of them is orthogonal. This orthogonality, you can almost think of it as coming at a price. Here, C, the Hessenberg matrix, is highly structured. Up here, we have orthogonal Q, but H is Hessenberg, and we lose that structure. And then this has a parallel. Need a little more room here. This parallel is pointed out in Trefethen and Bau's numerical linear algebra textbook. I think this is pretty neat. If you look at the Schur and Jordan decompositions of a matrix, okay. These you can think of as diagonalization or eigenvalue decompositions, spectral decompositions, but not quite, because it really depends on whether or not A is symmetric or how normal A is. Okay, so what I want to emphasize here is that in the Schur decomposition, these exist for any matrix, any square matrix A, and these exist for any square matrix A. Although the form of a companion matrix might become more complicated. Well, never mind. So in this situation, T is upper triangular, and its diagonal entries contain the eigenvalues of A. So it's upper triangular, and it contains eigenvalue information. And then U is unitary. Okay. And then down here, J consists of Jordan blocks, which are upper triangular, but they're more than upper triangular. They're upper bidiagonal. And so the parallel I want to point out is that down here we have upper triangular matrices, but J is highly structured. Jordan blocks are far more structured than merely being upper triangular. They're also upper bidiagonal. So upper triangular, but structured. Upper Hessenberg companion matrices are structured. Down here we have unitary similarity transformation. Up here we have unitary similarity transformation. And I think those are all the connections that I wanted to draw. Oh yeah, both of these also contain eigen information. So upper triangular with eigen information, whereas these are upper Hessenberg. And then these are, the similarity transformations are bases for the Krylov subspace, whereas down here, the Schur vectors and the Jordan vectors might be eigenvectors. Assuming the particular eigenvalues have enough eigenvectors, or the eigenspace has high enough dimension. So some neat parallels there. And the last thing that I wanted to talk about briefly is to point out a special case of the Krylov matrix, and that is the Vandermonde matrix. And talk about it in the context of the facts that we just looked over. Vandermonde matrix for a particular set of scalars, W, is as follows. It's the matrix W, it's the n by n matrix W, such that the jk entry is scalar j raised to the k minus 1 power. So it looks like this. When k is equal to 1, we have all 1s, and then we have W1, Wn, W1 squared, Wn squared, Wn to the n minus 1, Wn to the n minus 1. Cool. And the neat thing, one neat thing I think, is that this is exactly equal to the Krylov matrix, where the matrix is the diagonal matrix with the scalars on the diagonal, and the vector is the vector of all ones. So a Vandermonde matrix is exactly equal to a Krylov matrix, which I think is kind of neat. So a quick corollary from that is that we have the same relationship between the companion matrix for the characteristic polynomial for this diagonal matrix. We have this same relationship as discussed before for all Krylov matrices. So, in other words, if this Krylov matrix is invertible, then this proves, once again, that the companion matrix has eigenvalues exactly equal to the roots of the polynomial for which it is the companion matrix. So let me write out the specifics here. First, this is W, the Vandermonde matrix. Second, C is the companion matrix for Px, the characteristic polynomial of lambda. But the characteristic polynomial of lambda is simply the polynomial having exactly the roots equal to these scalars, because those scalars are the diagonal entries on the diagonal matrix lambda. Okay. So if the Krylov matrix is invertible, if the Vandermonde matrix is invertible, then this provides a proof that the Vandermonde matrix, or this particular Krylov matrix, diagonalizes the companion matrix, which is pretty neat. From here, there are two other points that we don't have time for. One is that you can use this to do polynomial interpolation. Here, we know how to construct this Vandermonde matrix given the scalars lambda. I should say this is a weak form of polynomial interpolation. So we have a Vandermonde matrix, we know what lambda is. We don't necessarily yet know what the polynomial coefficients are for p of x. Well, if you form this, then you can back solve the rightmost column. So if we look at the rightmost column of this, the rightmost column of this is simply lambda the n times e. Yeah. And then the rightmost column of this is simply, I called the vector p before, where p is the rightmost column of our companion matrix. So this vector contains the polynomial coefficients for the characteristic polynomial of lambda. So back solving this, where this is a vector, because this is a diagonal matrix, we can compute this vector easily, and then we can compute the Vandermonde matrix easily, and back solving would get us the polynomial coefficients. This is a terrible idea in practice because Vandermonde matrices and Krylov matrices are ill-conditioned, but it's neat to point out. And then the second point we don't have time to get into the details of is that you can do polynomial root finding using the companion matrix. If you know the companion matrix and you can diagonalize it, then that will get you the roots in lambda. So finding eigenvalues of such a matrix is a stable operation that you can do somewhat efficiently. There was a recent paper by Professor Jha in the math department here on doing exactly that. It turns out that this is a very structured matrix as you do Francis QR iterations on it. All right, thanks.